Hello, welcome to this video. Now we have talked about speed in a circular motion. We also talked about the velocity in circular motion, and this time we're going to look at a circular motion that's happening at constant speed. So when something a circular motion happens at constant speed, we call it uniform circular motion. So that's the name for this kind of motion. And I worked out numbers this time, so this will be different than some other times. We'll look at a circular motion which radius is 0.5 meter, and the speed at every instant is the same. It's not just the average speed, it's the speed at each instant is same. So if I draw the velocity vector here, I will get same size arrow. Okay, over here is the same size arrow. Point that way. 3, 4. So you get same size arrow. Representing. Remember that the size of these arrows represent the magnitude of the velocity vector. So if this is velocity A and this is velocity B, it's going to be this vector will represent velocity A and this vector will represent velocity B. Okay, so now you can see even if the speed was same, there is a velocity difference. If you can actually figure out the average acceleration between this point and that point. So let's if you draw this, so if I say velocity at that point minus velocity at that point divided by the time it takes from A to B, delta t, it takes this is the average acceleration. Between A and B. But this is the definition of average acceleration. How much velocity changed, or how much time it took. You can use a arrow method for getting this different. Even if you don't use analytic method with x and y component, you can do actually this way. So you can have both arrows A and B come out of the same point. So the VA comes out like that, and so VA comes out like that, and the VB will be coming out like this, same size. And this will be the VB minus VA direction. So average velocity is pointed in, you can see it's in, if between here and here is pointed in this direction. That's the direction of the change in velocity, and this is a positive number. So if you take a ratio of these two, you're going to be this will be the direction of the average velocity. I'm sorry, average acceleration. I misspoke. So this is the direction of average acceleration between A and B. You can get an acceleration around a particular instance, like over here. What's the acceleration around here? Well, we'll have to take a very close to it what the velocity vector looks like, and then take a subtraction of these two. So if you say, well, I really want not average acceleration, but acceleration at an instant. So instantaneous acceleration. So if you do that, so I want acceleration at this instant. So this is at t, and I want acceleration here. Well, what you'll have to do, take a very close to this two of this kind of V and VB. So if this is A, you have to do B right next to it. Now when you do that, VA looks like that, same as old. VA looks like that. But the VB is very close to that. Actually, it's almost the same thing as that, but just almost here. So that's the VV. The difference is the same way from go to the tip of A to the tip of B. So if you look at which way the acceleration is pointed towards the center. Right at A, the acceleration is pointed. This direction is direction towards the center. So that means the change in velocity that occurred here. This is VB minus VA. And if this is a very small amount of time now, this is delta t, this is a t plus delta t. So if I divide this by delta t, I get the acceleration that's occurring over here. So this means the acceleration in this case, acceleration in the case of constant speed, acceleration in the case of constant speed, motion in a circle is actually towards the center. Towards the center, you can say centripetal. Centripetal. And so this acceleration is called centripetal acceleration. So centripetal acceleration. So now that we have a direction of the acceleration at a point, not average, I'm over here, I want to know what's my acceleration. Its acceleration is towards the center. Then I want to know what's the magnitude of this is. Well, that's actually a very difficult calculation, but we know the formula for that. We will use a symbol AC to denote this kind of acceleration, the magnitude of this. So the direction is that's the direction, and the magnitude has a formula that you should memorize. So if it's going at speed v, it's going at this instant at v, then it's going to be v squared, and if the radius is r, so v squared over r. So the direction is this, and magnitude is that. And so that's the formula of centripetal acceleration. So let's look at numerically what would have gotten over here. So we had this thing was going at 4 meters per second, and it was from the center, it was half a meter. So in this case, the direction of acceleration is just that way, and the magnitude is v squared over r is 4 meters over second square over r was 0.5 meter. And so when we have a 16 meters square over second square or 0.5 meter, and that's 32 meter over second square. You can see this is almost 3 times as large as g, and it is a really easy to get very high acceleration in a circular motion very easily. So I will stop here. Next we're going to talk about what happens if you don't have uniform circular motion. When you don't have uniform circular motion, meaning speed is changing at different points, you have a different speed, which means your centripetal acceleration's value will itself be changing at different places. You'll have a different value. In addition, you're going to have an acceleration that's going to be not just towards the center, but also along the tangent, and that will call tangential acceleration. So right now we have a centripetal acceleration. When there is a non-uniform circular motion, you're going to have another type of acceleration in addition to centripetal acceleration. So that will be the next video is going to be so-called tangential acceleration. And so see you in the next video. Bye.